neighbor is pushing a 35 kilogram lawnmower up a 6.2 degree incline, theta 1, check, at a constant rate of speed in a straight line. The pushing force being applied is 256 newtons along the direction of the lawnmower handle. Okay. Looks like someone just drew a car and then like a line there. Lazy. Or efficient, I'm not sure. Theta 2 is 19 degrees from the plane of the four wheels. What is the magnitude of the force of friction against which the neighbor is pushing the lawnmower? Okay, so some assumptions we're going to make here is that the wheels aren't rolling, because I think we'd have to take some other things into account there maybe. I don't know. And even then, like when you have wheels and friction, usually the wheels, yeah. So what I'm going to assume here is start drawing some pictures. So we have a force gravity going down like this. So we have force gravity. And I'm going to redraw this as, I can do better than that. There we go. This will be force gravity in the x direction. And this will be force gravity in the y direction. That force gravity in the y direction is going to be, and I have my axis tilted so that it's parallel with this ramp here. That's going to create a normal force. And then we're going to have a force of friction. I'm not really sure where from. I'm going to say it right from here. Force friction. And then we're going to have a force push going this direction. So we have a, I'm going to draw it like this as a force push y, force push x, and then there's going to be a force normal. One force normal will be due to gravity, and another force normal will be due to pushing in the y direction. Okay, I know, lots and lots of arrows. The concept I'm trying to get here is we have gravity pulling it down, and we have a force pushing it forward, and we also have friction holding it back, resisting motion. So since we're told that we have constant speed, so if we have a constant speed, that means the acceleration equals 0, which means the sum of all forces, which is mass times acceleration. That means that the sum of all the forces are going to cancel each other out. So we have forces, what I call in the x direction, up and down the slope, and then we also have forces in the y direction, which is perpendicular or normal to the slope. Start by writing a balance out of all of these forces. So we have force Gx right here, which is pulling down. Now, if you've done enough blocks sliding down a ramp problems, you know that that's going to be mg sine of theta, pulling it back. Then the direction of motion is up, so we're also going to have force of friction going backwards. And that is going to be set equal to force pushed in the x direction. So force pushed in the x direction, so we have a theta here. So to find this component of it, that's going to be whatever the force pushing is times cosine theta. The reason we have cosine, I'll erase this excessive number of arrows. So we can look at this as a vector going this direction. I know it's the opposite, it's actually being pushed down. We can say the opposite as long as we understand. So we then have theta here that we're working with. So to find this component of the vector right there, that's going to be the cosine of theta times force applied. So this is our first equation. Now let's see what we got here. What is the magnitude of the force of friction against which the neighbor is pushing the lawnmower? So I'm just going to start solving this because I think we know most of this already. We might not even have to solve the other dimension. So we know what the mass is. We know what gravity is. We know what theta is. I'm going to change this to, let's see, this will be theta 1. This will be theta 2. We know what theta 1 is. We don't know what force of friction is. What is the magnitude of the force of friction? We don't know what that is. We know what the force pushing is. and we know what the cosine thing. We might actually know everything here. So here's what we're going to do then. Force of friction equals force pushing cosine theta minus mg sine of theta. This will be theta 2. This will be theta 1. Force pushing, we're told, is 256. So we have 256 times cosine of, we said it was 19 degrees, minus mass, which is 35, times gravity, I'm going to call it 9.8. And then we have sine of 6.2. This might be easier than I thought. Bump, bump, bump. So, go to the calculator. On clear mode degrees, 256. Wait a second, actually make sure I got it in degrees. I am. 256 times cosine of 19 minus 35 times 9.8. I'll throw in a 1 just for good measure. Times sine of 6.2. That gives us 204.97. And that will be newtons. So let's see here. That should be less. Yep, so there's more pushing. So it makes sense that force of friction is less. Yeah, I think that's all we need to do for this problem. That's not too bad. To kind of reiterate here, what we did was we looked at the forces and how they balance each other out. So if we have a constant rate of speed, it means no acceleration, which means all forces have to balance. Basically, the forces going left have to equal the forces going right. In this case, I call it left downhill, right uphill. So downhill, they were mg sine theta, and then force of friction. Force of friction always opposes the direction of motion, since we're being pushed uphill. And then uphill was due to the force applied being pushed. We knew this angle, and we knew cosine of theta, so we knew how much force is being pushing uphill. Set those equal to each other, and then we just solved. One thing that you might see with these kind of questions at some point is force of friction. That is normally mu, which is coefficient of friction, either static or kinetic, times the normal force, which when you're talking about a block diagram like this will normally be mg, a block sliding down a ramp, mg cosine of theta. And then you kind of calculate that in. But they didn't even ask us for that this time. They just asked us for the force without giving us mu or anything like that, which is convenient. So that is how to approach this problem. Hope it helped. See you next time.